Basically, EEG is a measurement of the fluctual electrical potentials or electrical signals produced by the brain. And the fluctuations in voltage are specified by their magnitude or their amplitude. And this can be measured in microvolts, which is a millionth of a volt. And that information, that millionths of a volt information, has to be amplified for us to be able to use it in a useful manner. Now, most of the time, the waves that we're measuring, so the information that we're measuring with the EEG, is measured from the scalp and coming from the cortex of the brain. Now, we will demonstrate how we can look at the functions of deep cortical structures a little bit later in the presentation. It's important to realize that the amplitude or the magnitude of the measurement is a direct result of the number of neurons that are firing under each electrode. So the amplitude of the EEG can also be a direct reflection of the number of neurons that are activating at any given time underneath any given electrode. Now, the graph that's produced with a standard EEG is a graph that looks something like this. And each one of these lines is a different electrode, and each one of these lines is a complex waveform. And by complex waveform, I mean that it has many different frequencies of waves to compose this complex waveform. And so one of the first things that we want to do is to separate out the different frequencies that are contained in this complex waveform. And it turns out there are ways to do that. So the way in which we do this is that we use computers to perform a function called fast Fourier transform. And the fast Fourier transform will be able to take a complex waveform and transform it into the components of the different frequencies that are involved. So what we'll see is it will give us a head map that looks like this, and we call these topographic head maps. And the frequency range is listed at the top. Okay, so the computer's done its job. It has isolated out the delta, the theta, the alpha, the beta, high beta, gamma frequency ranges. Okay, and then we've asked the computer to plot them on the head map according to a scale at the bottom that shows the blue activity on the left and the red activity on the right. And these are indicating activity levels of plus or minus 3 standard deviations. So when it's dark blue, it's minus 3 standard deviations, and when it's bright red, it's plus 3 standard deviations away from the norm, basically. So from that, we can get an idea of where in the brain there are areas of low functionality and high functionality. And by high functionality, we mean dysfunctional high functionality. So it turns out that too much activity and not enough activity are both not good in the brain. So we need an appropriate level of activity. And then we can see that these areas of either low or high activity or normal activity that are being demonstrated can be then looked at across the different range of frequencies. Okay, so we can see that in the alpha frequency, there's an area here that seems to be engaging in too much alpha activity. There's in the beta 3 frequency, we can see there's an area here that's not engaging enough in beta 3 frequency. So this is all very interesting, but it's also needs a bit more information before we can totally use it to help patients. Now, this is just a diagram demonstrating what we're actually measuring with the EEG. So those blue and red and green areas on the head maps represent activity of these neurons. So basically the pyramidal neurons in the cortex, and each electrode is probably picking between 4 and 10,000 neurons, depending on where in the cortex it is placed. And if we look at how these complex waveforms that we see on the EEG that we then take apart or disassemble and put into different individual frequencies, they come from the generation of action potentials down here. So this is a micropipette measurement just outside this neuron, which is showing the action potential activity. Then there's another micropipette placed further away from the neuron, which then starts to involve the activities of other neurons that are in that area. And that produces what's called a local field potential. And the local field potential, you can see if you look at the lines of the local field potential and the actual complex waveform of the EEG, they start to become very similar. And in fact, they, when we isolate these down, absolutely reflect exact activity of action potential firing from the neuron through the local field potential into the complex waveform. So this is the electrode outside the scalp, and this is this is the electrode outside the scalp, and this is going back to the amplifier because that signal has to be amplified before we can have any meaningful use of it. Now, this is a diagram just showing the flow. So we have the initial EEG activity being measured from electrodes on the scalp. That goes through the computer and forms this complex waveform. So this is this goes through the amplifier and forms this complex waveform. Then it goes through the computer where we form the fast Fourier transform, and we get the individual frequencies out of it, and from the individual frequencies we can get a production of a topographic head map, which helps us in a two-dimensional way see what's functioning inside the brain and which frequency levels are more within the normal range than others. Now, that information, so the information from the EEG can be further utilized or further massaged to give us an indication of what's happening in deeper areas of the brain. And this is Roberto Pascal Marquis. He's the mathematician who basically developed low-resolution electromagnetic tomography, or LORETA. And LORETA is a way of calculating what is known in mathematics as the reverse solution. So if, for instance, we took a balloon, and inside the balloon we put a battery, and then we slowly move this balloon around, and we said all you could measure was the information that you can gain from the surface of that balloon about the position of that battery, you would have to be able to figure out how the changes in the field would be represented on the surface of the balloon. And basically that's what Roberto has done. He's calculated the formulation that will tell us that if this particular field is detected on the surface of the skull, then that will mean that these areas can be generating deep inside the brain the signals that are producing that pattern on the scalp. So basically, low resolution does not mean low accuracy, because it's very accurate. But low resolution means that it is involving a larger area on the cortex than something like MRI would be able to focus down on. But MRI is not actually measuring functional activity. It's not measuring electrical activity. It's looking more at morphology and anatomy than it is in the actual change in current flows. So Loretta helps us, and it helps us a lot, because what Loretta can do is it can tell us where in the brain the worst areas of dysfunctional activity is happening. And so we can look at the Loretta in a two-dimensional format. So we see these Lorettas are printed or signified on a head map that looks a lot like an MRI, and that's because this is an MRI head map. So these are the same head maps that were developed at the Montreal Institute that are used worldwide in a worldwide system to normalize what MRIs look like. So that's why they look like an MRI, but they're measuring different stuff than an MRI. So they're telling us where dipolic dysfunction is happening and where we can determine where those areas are that are the worst and areas that are not so bad. So from the head map, we now get this two-dimensional Loretta, which then narrows down where things are happening in the brain, where the most dysfunction may be. And then from this, we can actually translate that into a three-dimensional brain structure or three-dimensional brain image. This is very important because we can now use the dysfunctional areas associated with Brodmann areas. So Brodmann areas are areas of the brain that were basically defined by this German anatomist, Corbinian Brodmann. And in the early 19th century, he meticulously dissected different areas of the brain and used a Nissl substance or Nissl stain and identified different structural areas. So areas that differed morphologically on the surface of the cortex or in the cortex, and then surmised that because there was a different morphology, then perhaps there was a different function in each of these areas. So he went on to identify what are now widely known as the Brodmann areas of the brain. And as you can see, there are slightly different areas on each side of the brain, and slightly different areas in the deep cortex of the brain. But for the most part, what's on one side is on the other. They just have different functions, it turns out. So let's just look at some of the different common areas that you might come across in your practice. So the Brodmann area 11 is probably one of the main constituents of the orbital frontal cortex that we've been talking about a lot. So the orbital frontal cortex is one of the main components, say, of the functional projection systems for executive function. And it is interesting because this part of the brain, or this part of the executive function, is processing emotions and giving value to those emotions. Now, if we look at Brodmann area 46, this is the dorsolateral prefrontal cortex. Again, one of the main areas that we usually involve in the executive functioning. But this is more an area that's processing cognitive information and working memory. So we have the difference between Brodmann area 11 and Brodmann area 46. And now Brodmann area 47 is even more complex because it's related to the feeling of empathy towards the story contents of others. So when someone's telling you their story, this area is responsible for activating the pathways that allow you to perceive empathy, which is an emotional aspect of this area. And it's also activated automatically or in a reflexogenic fashion. So you really can't have control over this area so much. But in contrast to that, area 46, which is involved with willed action or action that you can control, it's a important difference between those two areas. And in the left hemisphere and the right hemisphere, area 47 does a little bit different stuff. So in the left hemisphere, it's playing an important role in the syntax of language. So understanding when a verb is necessary and a pronoun needs to be in front of this and that. So understanding how to communicate in your language, so your syntax of language, is on the left area 47. On the right area 47, that's where you put the emotional component into the story of others. Now, I'll just take you back and we'll review where those areas are. So here's area 46, okay? Area 46 is here. Area 47 is hard to see on this map because it's in a little bit deeper aspect. But let's see if I can find you area 11, which is right here. Okay, so we got area 11, area 45 and 46. So you start to see that these are all areas in the frontal area of the brain, the orbital frontal cortex and the dorsolateral frontal cortex. Okay, so now you understand why it's important that we can find through the EEG and through the Loretta where areas of the brain are dysfunctional. And now we can actually map them onto a Brodmann area, which allows us to have a pretty robust prediction of what dysfunctions in this person's brain would bring about as far as behavioral deficiencies or behavioral dysfunction. Now, let's talk now about the rationale for using an EEG. Now, you can use this process, okay, this template for any treatment that or any diagnostic test you're using, because you're at some point you're going to be asked to demonstrate, either by request from a parent, request from a patient, request from a regulatory authority, why are you using this test? Why are you using this treatment? Why are you prescribing this treatment for so long? So you have to develop a systematic approach to demonstrating what your rationale is for the use of all of the modalities you're using in your practice. So basically we start off and we say, well, what is in the literature that says that this form of measurement can help us in detecting things that we couldn't detect otherwise? So basically in what's coming out in the literature is that a lot of these children who have developmental delay, including developmental coordination delay, may have seizures. Now, the seizures may be not visible seizures, and we'll talk about that in a minute, about the difference between visible seizures and non-visible seizures. And so we call these seizures that are not clinically visible isolated epileptic discharges, IEDs. And the IEDs basically are occurring in a large number or percentage of patients or children that are showing these developmental delays. And it's important that these IEDs can only be detected with an EEG. So you can't detect them for the most part unless you're an extremely good clinical observer and you're extremely lucky that the seizure happens when you're actually examining the patient. So there is a specific example of where an EEG is actually essential in understanding whether these IEDs are happening or not. And one of the things these IEDs can do is they can form these functional disconnections, functional disconnection syndrome, which then leads to developmental delay and problems with behavior. So you start to see the connection now between the theory that we talked about and now the clinical symptoms of presentation, and now the diagnostic tools that we're using to figure out if these things are actually happening in the child. Now, the IEDs basically represent an epiphenomenon of cerebral dysfunction, or an underlying cortical morphofunctional abnormality. So what does that mean? It means that sometimes the change in activity that's happening through these seizures can result in a change in the actual anatomy. So that the change in the synaptic map is happening in the child. So that's where the morphofunctional abnormality comes from. It's also a functional abnormality, in that it produces these functional disconnects when these networks try to connect. They can't because of the disruption that these IEDs are causing, and it starts to affect the progress of development. It starts to affect the timeline of development, and eventually they start to lag behind. Now, some of these IEDs are insufficient to produce an epileptic seizure, or a seizure that we can see. So if we look at the little triangle here, or the pyramid, there is a level of hyperexcitability that is not enough to generate an IED. Now, usually we can measure this. So we can measure hyperexcitability that's not producing IEDs with an EEG. If we know how to read those head maps, we can identify those areas of hyperexcitability, even though they're not causing any kind of seizure disorder. Then there are IEDs that are not detectable at the scalp. So in other words, even though they are happening, we can't detect them with an EEG because they're not detectable through that type of measurement, that type of modality. Now, we also have scalp detectable IEDs. These are the ones that we can see. We can say, oh, this child is having IEDs. There they are. We can demonstrate them. And then there are the actual seizures that these IEDs can produce. Now, the seizures are seizures you can see clinically. Okay, so you can actually see the child in repetitive movement patterns. You can see them drift away as their eyes drift away. You can see them lose their stream of consciousness for a few seconds. Or you can see their tonic myoclonic seizures where they're actually shaking and falling to the ground. So the seizure you can see. Okay, scalp detectable IEDs we can see because we can detect them on the EEG. Scalp undetectable IEDs we really struggle to identify, and sometimes we question them, we query, are they IEDs, are they not? And that's what happened in the original EEG this child had, is the technician or the epileptologist couldn't tell whether they were IEDs or not. And then there is this area that is hyperexcitability, but not IEDs, but we can actually see that. So lots of times we will say there's the hyperexcitability is a potential IED production area. Okay, so that kind of explains the seizure production pyramid. So now the interesting thing is that IEDs are also blocking maturation, and they're producing transient cognitive impairments. And the isolated discharges have a higher prevalence in childhood psychiatric disorders as compared with healthy children. And so in other words, when we have children with psychiatric disorders and we look at their EEGs, we see a higher percentage of IEDs in these children. And specifically, we see them with a much higher percentage in autism spectrum disorders and attention hyperactivity disorders, and even Tourette's syndrome. So there is starting to be a real solid reason for doing EEGs on these to try to differentiate what's causing these situations in kids. So just a review about the frontal striatal network, because this is really the message we're trying to hammer home, is that basically all of these networks are formed partially from different areas of the brain. And so we can see that in order to actually have a complete and functional frontal striatal network, you have to have connectivity between all of these areas, and that connectivity has to happen within a specified time range. So we see IEDs and functional disconnection, toxic exposure, all these things can delay the speed at which these networks can form and then result in behavioral problems. And the behavioral, the cognitive dysfunction that starts to happen starts to delay the degree at which and the speed at which and the architecture of development of these networks, to the point that they start to slow down in their behavioral expression of certain things. So now we start to understand the connection between the formation and development of these distributed systems and the timeline of observational maturation that we see. So it's very intriguing to me, and it's very exciting to me, that we're at the point now where we're starting to understand these things a little better, and we can start really helping people and children that maybe 10 years ago we couldn't help because we didn't understand what was happening. Now, I'm not saying we understand the whole process yet, but I'm saying it's an exciting time to be in healthcare, an exciting time to understand neuroscience and to understand how to apply that, especially in a pediatric population. Now, the other component that I want to talk about is this concept of cortical asymmetry. And I've been writing about this for a long time and doing research on this for a long time. And the concept of cortical asymmetry used to be that there was a difference between the right and the left brain because, for instance, the language processing area was on the left and the emotional processing area was on the right. But we now know that asymmetry can happen across the formation of these connection networks. So in other words, when an attentional network forms, it forms, but the side on the left cortex is different, or uses a different pathway, or uses different neurotransmitters, whatever, that delay or change the response level of that side so that we get an asymmetric formation of our network. So the asymmetric formation of the network, if it's bad enough or if it's severe enough, can result in formation of dysfunction of what that system was made to do. So if that system was made to form a memory, that memory will be distorted. If that system was made to experience love or an emotion, then that will be distorted. So this is the new progression of cortical asymmetry. Now, the interesting thing is that we've been using cortical asymmetry a long time in functional neurology to correct a lot of the symptomatology. We just didn't really understand how it worked. And the original studies by Carrick in this area, where he was talking about blind spot developments, and were really, really challenged and really, really castigated in the scientific field. And now people are coming around and saying, wow, this is, look at this new stuff we've discovered. And we've been using it for a long time in functional neurology. So it's interesting how the narrative changes depending on who does the discovering. So basically, when we have asymmetric development of networks, we know the asymmetry because we've measured these. I published some papers on depression and asymmetry a couple of years ago, and presented at a number of conferences on a variety of different conditions. But ADHD, developmental delay, emotional control disorders, autonomic dysregulation, and balance disorders are all highly implicated or highly comorbid, I suppose is a good word, with cortical asymmetry.